So this is EE698G, lecture 21. This is our third discussion session on oscillators. Okay, so we started by taking a look at a feedback system. And we found that in the absence of any input, if this negative feedback system has to oscillate, what is the condition? Magnitude of h of j omega naught. So we are trying to design it such that it oscillates at omega naught, in which case the magnitude should be equal to 1 and the angle should be equal to plus or minus pi. Then we said that because we know we are dealing with system that has non-idealities and we expect that the gain is going to drop across PVT, instead of making it exactly equal to 1, we'll make it greater than or equal to 1. Right? And this was the condition we were working with. So now turns out this is necessary but not sufficient condition. So if you have a system that oscillates, it means that this condition is satisfied. But if you have a system which satisfies this condition, it's not given that the system can oscillate. Right? There are few systems for which the magnitude of h of j omega naught can be greater than 1 and angle at that frequency, the phase at that frequency could be plus or minus pi and it might not oscillate. Right? But in this course we will only deal with systems for which once these criteria are satisfied, we expect that system to oscillate. For those of you who are interested, an example that would fit this situation is a feedback loop with a feed-forward compensation. So if you are interested, you can check up on that. Okay.
So if we go by that method one of finding if the system oscillates or not, so that is valid for all of the systems which we cover in this course.
In this course, right? But the ultimate test, like given any system, if you want to check if it's going to oscillate, the ultimate test would be to check if the closed loop poles are either on the RHP or on the j omega axis. Or now to find where the closed loop poles are, you can do the brute force method and calculate the poles, or use root locus method, or check the Nyquist plot, etc. So there are various ways in which you can do. Okay, so then we briefly saw how ring oscillators can be analyzed, and we were moving towards LC oscillators. To start off, we looked at what is an LC tank. This is just a fancy way of saying that we have put an inductor and a capacitor in parallel. Right? So we were looking at the non-idealities associated with the inductor. So any time you implement an inductor, you will be implementing it with a real metal line, which means you will have some resistance associated with it. Earlier, when a current was flowing through the inductor, you don't have any power dissipation. Now in the presence of the series resistance, anytime a current flows, you have a power dissipation. Right? There is going to be I square R power dissipated across the resistor. So now our inductor has become lossy, right? And we want to quantify how good of an inductor we have. If we have a very good quality inductor, the losses should be minimal. If it's a bad quality inductor, the loss is expected to be higher. So to quantify this, we use the parameter called as quality factor. So if you have an inductor with a resistor in series, the quality factor is given by omega L, so omega Ls by Rs. Right? Now if this is a very good quality inductor, which means the value of Rs will be small, therefore the quality factor Q is going to be very high. Right? If it's a bad quality inductor, Rs will be high, therefore Q is going to reduce. Okay, then we started looking at a tank where you have the capacitance connected in parallel with this lossy inductor. And we said that it is going to be a little difficult to calculate whatever we need to calculate in the circuits when we have a configuration like this, and our life will be easier if everything was connected in parallel. Okay, so some LP, RP in parallel with the same C. So now we have to figure out how to replace this combination of inductor and resistor with this parallel combination of inductor and resistor. And you had started the calculation for this. So let me call this as some Zs of j omega. This will be some Zp of j omega. At some omega, typically this will be the oscillation frequency. We would like the Zs of j omega to be equal to Zp of j omega. Right? So what is the expression for Zs? So this is Rs plus j omega Ls, and Zp is j omega Lp into Rp divided by Rp plus j omega Lp, parallel combination of Lp and Rp. So I'll take the denominator and multiply. I'll take the denominator to LHS and multiply the factors. So Rs and Rp together will give you Rs Rp. The second terms together will give you minus omega square Ls Lp plus, now we'll look at the cross terms. You have Ls Rp plus Rs. So let me write it as Rp Ls plus Rs Lp. You can take this quantity also to the RHS. So you'll have minus Rp Lp equal to 0. Okay. Now to solve this, we equate the real and imaginary parts to 0 separately. So equating the real parts to 0 will give you Rs Rp should be equal to omega square Ls Lp. So I can find out the expression for Rp from here. This is simply equal to omega square Ls Lp divided by Rs. Okay, so let me call this as 1. Now I equate the imaginary part to 0. So I have Rp, I'll take the common terms outside. So this is Ls minus Lp, these two, plus Rs Lp is equal to 0. Substitute for Rp. So you get omega square Ls Lp by Rs into Ls minus Lp plus Rs Lp equal to 0. There is Lp on both terms, so I'll remove that. Now the quantity we want to find here is Lp. Can you give me the expression for Lp?
L plus R square by omega square.
This is okay. So just for completeness, I'll write the results here once more. So the result you get is Lp is equal to Ls and Rp will be equal to Q square times Rs. Okay. So let me give you a quick problem to solve. So you have a inductor with value 5 nanohenry. It has a series resistance of 20 ohm. Now you are expected to use this inductor in an LC tank where the oscillation frequency will be designed to be 5 gigahertz. Okay. So first part of the question is calculate quality factor, and second part is find the Rp equivalent. Find the Rp. So please try it. Okay. So now basically anytime you have a combination of L series R, you are now capable of making it into some L in parallel with RP. So the quality factor was written as omega L by Rs. Can you substitute and tell me how to write that expression in terms of RP? You know the relationship between Rs and RP? And substitute it and... So I want an expression for Q in terms of omega L and RP.
You don't know Rs.
It's some value of Rs.
You did not understand what do you want? You need.
So I have written Q equal to omega L divided by Rs. I want an expression for this as a function of omega L and RP. RP by omega L. Right? So the moment you have a parallel combination, this is resistance by omega L, and the way to think about it is, if the parallel RL was of very good quality, right, then what should be the value of RP? Very high, infinite, right? And your quality factor should also be very high, right? So that is a nice way to think about it. Anytime you are writing quality factor for an inductor or a capacitor, it's going to be a ratio of the desired impedance by the and the undesirable quantity that is coming along. Then you look at the circuit and see if quality factor is to be high, which means the element is supposed to be ideal, and then you can decide what should come in the numerator and what should come in the denominator. Is that clear? Okay, so now this equation suggests that your quality factor is going to increase as the frequency is increasing, right? Because it is proportional to omega L. The second equation seems to suggest the reverse. So where are we going wrong?
Dependence of Rs and RP on omega.
RP is, if I assume that Rs doesn't vary with omega, your RP is still a function of omega. Right? So that way the results are still consistent. You simply have to remember that RP is also a function of omega. Okay, so when we had a LC tank, an ideal LC tank, how did the impedance look like? So we plotted the magnitude of the impedance and the phase associated with the impedance. How did the magnitude look like? Around omega naught, it went to infinity, right? And then it dropped off like this. And how did the angle look like?
It was first 90 and then
omega naught minus 90.
Right. So it started off at plus 90. There was a sharp transition at omega naught, and then it became minus 90. So now you have a parallel resistance with it. Right? So L, C and some RP. How do you think this is going to change? Right. So to what value will it limit to? RP. So you'll see a result like this. What about the phase? So the at lower and higher frequencies you expect it to be similar, but just that the slope around this region is now going to increase, right? So can you, if I had to predict what the slope of this phase function is, how would I do this? Just tell me the brute force method. Differentiate what? Why with respect to RP? So with respect to omega, you need to differentiate the phase function, right? So just for completeness, let me give you the expression for z of j omega. So this will be equal to j omega L RP divided by RP into 1 minus omega square LC plus j omega L. Now you can calculate the phase of this, as the numerator is going to give you pi by 2 minus So now you can differentiate it with respect to omega and substitute omega equal to omega naught and solve for this. So I will give you the result directly. This will be equal to minus 2 times Rp into C. Right? So this is proportional to Rp. Right? So as your Rp value increases, the slope is going to become sharper and sharper, becoming infinite when the Rp value is also infinite. Okay. So now what we'll do is,
It doesn't depend upon L.
You can go through the derivation. Right now, no, it doesn't. So because you are solving it for omega naught, right, you can replace C with L also by relating it to omega naught, right? So
Then it will be a function of omega naught also.
then it will be a function of omega naught, but your Rp, right now we have not assumed Rp to be a function of this. This let me check and get back to you. But I would expect that it is related to both C and L in some way.
Usually that only makes sense.
Yeah. So I can get back to you on the result. Okay. So now what we are going to do is, we have an impedance, right? Anytime, whenever we designed a common source amplifier, we had to load it. We had a transistor which was loaded by some impedance. So what happens if I load it with this LC tag? Have you seen circuits like this before? No? Okay, good.
I've never seen inductors in my life.
Right. So let's start with a very basic common source amplifier. I have V in here, V out here. So I'm interested in plotting the magnitude of V out by V in and the phase associated with this V out by V in transfer function. How does the magnitude look like?
GM into R.
Gm into R. So some gain, it's constant, right? How does the angle look like? Minus 180. Because of the negative sign you get as you go from 0 to the output. Okay. So now let me consider some capacitance at this node. How does V out by V in change? This is going to drop, and where would be the 3 dB frequency? 1 by RC. How does the phase plot change? Minus 180, and this RC is now going to contribute 1 pole, right? So you will have one more minus 90 on top of it. So it goes from minus 180 to minus 270. Okay. So now we'll repeat the same thing, just that instead of the resistor there, I'm going to add the LC tag. So I have L, we'll assume that we have a parallel resistance, and C. Right. So this is my V in, this is my V out. Now of course I can have a capacitance from here to ground, but in small signal model this node is also going to be grounded. So if this is some C and this is some CL, C and CL are coming in parallel, so effectively I can just model a single C with the total value. Similarly, I could have some R on across this. I will simply combine this R on with this resistance. Okay, so you have an L, R and a C like this. To be clear, I'll write it as RP. Okay, so the relationship from input to the output still remains sort of the same, right? V out will be equal to, you have a current flowing like this, that current is flowing through this load, so it is minus Gm times the impedance of this, and this is your gain. So now I want you to plot V out by V in magnitude as well as the angle associated with this V out by V in.
The thing is drawn up. Phase with the magnitude is the same.
The shape remains same.
Yeah. And
The shape remains the same.
Shape remains the same. Just multiply by GM.
Multiply with
When you say shape remains the same, what shape?
This one, but
the shape.
Of the LC tank, right?
uh-huh.
Yeah. So the shape is now going to look like this.
And that will shift by 1 minus 180 down. Phase is
So
minus 272. No, not minus.
what is this value?
GM into R.
GM into RP,
That.
right? And this is happening at your oscillation frequency. What about the phase?
Minus 90 to minus 270 with the same error.
Correct. So earlier it was minus 180 to minus 270, right? But now you have introduced a plus 90 and minus 90.
A 0 at the origin.
And 0 at minus 90.
Sorry?
If we shift the 0 axis to minus 180 and then just superimpose that graph which we got for that phase.
So from minus 180 you have to add a plus 90.
Yeah, so it's like basically we are shifting the 0 axis to minus 180 and then superimpose
Correct.
that graph.
Yeah. Right. So this goes from minus 90 to minus 270. So at omega naught, what do you expect the phase to be?
Minus 180.
This will be equal to minus 180. So far, okay?
Yes.
Right. So then let me give you a question.
Omega naught is equal to that. Under
So let's say you take a LC tank with values L, C, RP. At the input, let's say you bias it at some 500 millivolt plus some 20 millivolt into sine of omega naught t. You have to sketch how the output is going to look like, both the DC as well as the small signal riding on it. You are given that GMRP is equal to 5. Right? So you can assume that VDD is equal to 1 volt. So this RP is the inductor series resistance modeled as a parallel resistance. You have to plot the total voltage at V out. So of course the first part is to find out the DC bias at the output. Now in looking at the DC bias, this model of L and RP coming in parallel is not correct. We have calculated this for a particular frequency, right? So for looking at DC bias, this is some VDD, inductor in series with a resistor RS and a capacitor, right? Now I am still going to make an assumption here. I am going to assume that RS is a very small value. Technically you will have a drop across RS given by whatever is the bias current times RS, right? But if RS is a very small value, that drop is also going to be very small. Now in that case, your inductor is a short at DC, capacitor is open, so your output voltage is still VDD. Is that okay? Okay. So now you can look at the small signal model. So this is the bias point of the large signal picture. In the small signal model, at omega naught, you will simply have RP here, right? And then you will have a current flowing through this given by GM times VM. Therefore, this will be equal to minus GM RP into whatever is the input given, which is a 20 millivolt sinusoid. So now if I look at the input and output, your input was biased around 500 millivolt and this was a sinusoid with amplitude of 20 millivolt. Your output is now biased at 1 volt, which is the VDD. And you will have inverted sinusoid with much larger amplitude. So the amplitude will be equal to, what did you get?
0.1.
Yeah, 100 millivolts. Right, so this is a very nice point. You are able to get signals which are swinging much higher than the supply voltage. Therefore, even in low power circuit, this sort of a configuration is sometimes used because you can get better swings even when you are operating on lower power. Operating on lower supply voltage, you can still get signal swings that are higher than VDD. Any questions on this?
This is only valid when the small signal is operating at a frequency omega naught, right?
The value of RP is valid when you are operating at some given omega naught. If your omega naught changes, especially if it changes by a large factor, you need to recalculate the RP.
Like for example, in this input, the frequency of that small signal riding over 500 millivolts is omega naught. If it's not omega naught, then we can't say it like that.
Right. What do you think? Let's say the frequency given at the input. So this is I should draw it like this. Right. So now if you have fed in an input at a frequency very different from omega naught, what do you think will happen? It is going to get filtered out. Right. So the gain here is maximum when you are at GMRP. As you move away from omega naught, the gain is reducing rapidly. Right, which means if you are quite far away from omega naught, that signal is going to see an attenuation. The gain is going to be smaller than unity. Right, so any signal that is not around omega naught is going to get filtered out.
How is it getting filtered?
Because the gain is going to be smaller than unity at other frequencies. So the shape of this curve actually now depends on the quality factor of this tank. Right, so if you have L, R and C in parallel, then you can define the quality factor of the tank either by considering this L and R together. So you define it for omega naught.
We can get that amplification of the small signal only when we are operating close to omega naught.
Yeah, correct. So now what I was getting at it is, if you are working with a high quality tank, then this is going to be even narrower. Right, so you can get good tuning. Basically, you can get good selectivity if you are working with a good quality tank. So to define the quality factor of this tank, you can either consider L and RP together. So then at omega naught, this will be omega naught L divided by RP. Similarly,
RP by omega.
sorry, correct. This will be RP by omega naught L, because ideally you want RP to be infinite, right? Or you could consider RP and C together, right? In which case, what would be the expression?
RP to omega by C, something like that.
No. So think about it. So it has to be a ratio of RP, and the other factor is 1 by omega naught C.
Omega into RC.
So this will be equal to RP by 1 by omega naught C. So it will give you omega naught RP into C. Right. Now you can also substitute the value of omega naught into these equations. So omega naught is 1 by root of L into C into RP into C. Right. So this gives you the expression RP by root of L by C. So this way you can calculate the quality factor for the tank also. Now if the quality factor of the tank is very high, this becomes narrower and narrower. Okay.
So we get attenuation for
all the other frequencies and you get good gain only for omega naught. Right. So this is one way in which you can get a bandpass filter implementation. And we call this as a tunable load, meaning you can tune the frequency at which the load is giving you RP, and for everything else it is giving you very low impedance. Okay, so now you have seen how to construct a common source amplifier with a tunable load. Now we'll repeat the same thing that we did earlier. We'll take one stage, connect it in feedback, see if it can oscillate. Right? So our implementation 1 is this. So I take the output, connect it back to input. Can you tell me whether this can oscillate? So in
minus 90 to 90 only, right?
So here when we wrote the when we plotted the phase here, I already took into account this minus sign.
Yes.
Right? So if you are looking at minus h of s should give you minus 2 pi. Right? Because minus h of s is basically a minus sign is giving you a minus pi, and this h of s is giving you another pi. Right?
Here how we accounted it.
How did we account it? Okay. So I can take this example and explain it, right? You can also ignore the capacitance. The output is minus gm into r, right? So only because of this minus sign, your phase is at minus 180 degree. So that minus sign was accounted when we plotted the phase diagrams. So all that you have to look for is, if you do a loop like this, either going around you should get 360 degree so that it is positive feedback, or you have a minus 180 degree already here and you get another 180 degree here. So now depends on how you want to analyze. Either you look for the total phase shift within the loop, or you have a frequency independent negative sign and then you look for the phase shift being provided by this h of s.
So h of s is gm times z, right?
H of s is gm times z.
That can, the phase of that cannot go to minus 180.
Phase of that will go to minus 180. No, it doesn't go to minus 180. No, it goes to minus 180, not at omega naught.
Okay. Plus 90 to minus 90. GM times.
Correct. It doesn't go to minus 180. Right, so whichever way you look at this circuit cannot oscillate. So what is the next step we do? So one unit is not oscillating. What if we put 2 units and then put in feedback? Right? So let's try that. So we'll come to that. But for now, if you assume that it is not going to latch up, right? Then can it oscillate?
At omega naught, you get just plus 80 or minus 180 phase shift.
I want to know whether it is a 180 degree phase shift at omega.
Minus 180 degree phase shift.
Throughout. So if I go around like this, how much do I get?
It's minus 2 pi minus pi. Minus 3 pi basically.
So that is incorrect.
So minus 3 pi is equivalent to minus pi, right?
That is incorrect. Yeah. So now here.
Individually will give you minus pi.
Yeah. So here at omega naught, each stage can give you minus pi. Right? So now as you go around the loop,
the first is minus 3 pi, right?
No, this is giving you a minus pi.
Minus pi, sorry. Minus
Including
pi.
the negative sign,
Yeah.
right? This is also giving you a minus pi. So it's total minus 2 pi.
Okay,
So it's a full positive
I was talking
segment.
about the minus of H capital S that you used to write, right?
Right. So minus of H capital S together should have minus 2 pi. It has to be a positive feedback. So the full phase shift of 360 degree. Now here this minus sign is, let's say, a minus pi, and this H of S is giving you another minus pi. So either you look at the full minus of H of S as minus 2 pi, or you look at H of S giving you minus pi.
Okay.
So is this clear to others? You have a doubt?
Do it by finding the transfer function and then seeing it for if it can give a phase of minus pi.
That is what we have done now.
No, for the first stage, the transfer function is minus gm times z of j.
Sure. So for the first stage, the transfer function is, so you want this whole thing. This whole thing is what you would call as a minus H of S.
Equals to, I did the same way she did. I got minus 3 pi.
So this is some minus pi, and this is giving you minus 3 pi. Is that what you're doing?
That is giving you minus 2 pi.
This alone is giving you minus 2 pi.
Yes, and the total will be minus 3 pi. See, H of S will be the individual terms, right?
H of S is, yeah, correct.
Capital S will be H of 1s into H of 2s.
Correct.
So H of 1s has minus pi.
H of 1s has,
Minus pi.
The
no.
transfer function h1 of s into h2 of s.
No, it doesn't have minus pi.
h1 of s into h2 of s should be minus h of s because that's the total.
Correct.
Yeah.
This is equal to H1 of S into H2 of S.
Yes. Then take minus sign there.
Here is
You
H
can't
of,
take that minus sign there.
One second.
here is H of S minus G of Z. Just G of Z.
You calculate. So if I were to break the loop here and you go from here to here, whatever you get, that is together minus H of S. Right?
H of S comes out to be minus of
Ma'am, I found it for the capital just for okay.
1%. Yeah.
H of S comes out to be minus of GMZ whole square.
Yes. This will be GM square into Z of Z at j omega naught the whole square.
Yes. Now let me this minus will be minus 180.
This minus is not there, right? So this is now your correct. Fine. This is equal to your H of S.
Right. Now we will do for capital H.
This is
Minus
equal
minus
to
is
H
for
of S.
minus 180.
Okay. This is, let's say, minus pi.
Minus pi. Each z will give you minus 180 omega naught.
Each Z is giving you.
It will give me 0 because
It is giving you 0.
minus 90
Huh.
to minus 90.
So if I were to plot only for the tank, what did you get?
From 90 to minus.
The current plot you have is taking into account the negative sign. So if I plot only for the tank,
Okay.
let me, if I were to plot only for the tank, how would it look like? You have to put plus 180 to this.
It will be 0 at omega naught.
Correct. So this will go from plus 90 to minus 90 like this. Right? So this is giving you 0 phase shift. This will give you 0 phase shift. So H of S is giving you minus pi.
I got it minus 3 pi because that was already negative in one square.
If you say minus 3 pi, that is
We
fine.
multiplied minus minus and we made it positive. In the whole calculation in this, we made minus and positive one. So I calculated minus 3 pi is
Minus
also
3 pi is
minus
correct. But minus 3 pi is
equivalent to minus 5.
correct. That is equivalent. But so you have it is this minus sign and you had another minus 3 pi. So the overall phase shift in the loop is 4 pi for you. Minus 4 pi.
I will follow it. I will follow it.
Let me. So I'm sure someone else is also confused about this. Everyone else is clear? Then we will take it up at the end of the class. Okay. So earlier when we had directly a common source amplifier with a capacitive load, with 2 stages you were not able to get an oscillation. But a common source amplifier with a tank, LC tank, can give you oscillations even with 2 stages. Right? So now let me rearrange this for a little bit of aesthetics. Oh, before we come to that, quickly tell me whether this can latch up or not.
Anything, any other frequency will die.
Any other frequency?
It will die off. So the gain is less.
But is it positive feedback?
It's a positive feedback.
It is a positive feedback, right? What is the value of gain at DC?
GM
GM
square RS square.
GM into RS is the gain of each stage. Is that clear? At DC, you shouldn't look at the parallel resistance, right? At DC, you have to use the series resistance with the inductor. So at DC, your circuit simplifies to some RS connected like this. So the gain is now GM RS the whole square. Okay. So you have positive feedback with GM RS the whole square as the gain. Is it going to latch up?
Yeah.
Yes.
Why?
Latch up means it will go to VD, converts to VDD, right?
So whether it will reach VDD ground is basically the question. One node reaching VDD would mean that the other node is going closer to the ground. This will latch up? Can you tell me if this GM RS is going to be greater than 1 or less than 1? RS is a series resistance, right? So we would expect the RS to be a smaller value. Given that RS is not intentional, we would expect it to be a smaller value, right? Therefore, this is expected to be much smaller than 1, right? Okay, given that the loop gain at DC is smaller than 1, can you comment on whether this is going to latch up?
It would be at VDD by 2. It would be at VDD by 2.
It won't be at VDD by 2. Why at VDD by 2? Okay, so it is not latching up, right? It can oscillate at omega naught. Is that clear to everyone? Okay, so let's consider a system. Let's say the gain is some minus alpha with a minus sign here, so that when you go around the loop, it is a positive feedback alpha, right? We'll assume that we have given a DC voltage Vt, right? Then initially you will have Vt appearing here. I'm going to process this assuming a small delay in this unit, right? Now as it goes around the cycle, after this you will get plus alpha times Vt square, right? And if you go, plus alpha times Vt, now this gets multiplied by alpha, so you're going around the loop again and again. So I can write it as Vt into 1, second time you will get alpha times Vt, next alpha square times Vt, etc. it will go on, right? Now if alpha is much lesser than 1, this value will simply settle to Vt by 1 minus alpha. And the smaller the alpha is, the closer it will be to Vt. So it doesn't explode, right? If alpha was greater than 1, this becomes unbounded and it goes to infinity. In a real system, it would mean that the transistors are coming out of saturation and you are reaching the supply rates, right? So the condition is you either need to have negative feedback at DC, or if it is positive feedback, the loop gain at DC has to be smaller than unity. And given that the series resistance is expected to be very small, the circuit is, in practice, it's very easy to make sure that this doesn't latch up.
So in steady state, all the nodes will be at voltage Vt, right?
Where?
There won't be any.
Oh, so at if I consider a DC, right, it doesn't go to supply rates. Now, if I consider some omega naught swings, that will get a large gain in the loop and it will begin to oscillate. So as long as you can introduce some disturbance in the circuit, it should start oscillating at omega.
Small signals, okay, then we'll consider that Rp and then that GZ square.
Yeah. So anything at omega naught will see a loop gain of GMRP the whole square. Anything at DC sees a very small loop gain of GMRS the whole square. Okay, so now I'll take the same circuit and make it look very beautiful. So you have two tanks. I am simply going to reverse the direction of the mouse here. Where should I connect the gate to? Output of the second one. And where should I connect this to? Drain of this one. Right? So you can see that the input and outputs are cross coupled between the two stages. So what should we call this? Cross coupled oscillator. Right, and you can see that it has a pseudo differential behavior. If your output is increasing here, you would expect to see a corresponding decrease at this node. Right? So could you quickly tell me what would be the impedance of the circuit? So let's say I am looking up from here. Let me call this as Z1 of j omega, and I look down from here. So you are basically looking like this. Right? I'm looking up into the differential input, and I'm looking down into the differential input and looking up into the differential input points here. So I'll call this as Z1 of j omega. The bottom impedance I'm going to call as Z2 of j omega. So can you take a minute and see if you can calculate Z1 and Z2? I'll simply call these as L, C and RP, L, C and RP.
This is the same circuit as before, right?
This is the same circuit as before. So let me quickly explain Z1. So I'll do a general explanation first. Assume you have some impedance Z connected like this. Right? Now they are the circuit is pseudo differential in nature. So let me call this as, so if I assume that these nodes are Vx and Vy, right? So if I apply delta V, I expect to see a minus delta V here, right? So if I apply delta V, what is the current flowing through this? Delta V by Z, right? And in this you will have a current given by delta V by Z, but in the following direction, right? So this basically has symmetry around this point. Now I take another circuit where I have connected two impedances in series.
It's minus 2 by G.
Right? Now I repeat the same thing. I apply delta V here and I apply minus delta V here. What is the current flowing through this? 2 delta V by 2Z, right? Effectively that is still delta V by Z. And what is the potential here? 0. Why? So superposition plus linearity, given the symmetry, that will give you this condition, right?
That's pseudo differential, so we can just short all the points in the middle.
You can short all the points in the middle. Yeah. So basically you are taking delta V by Z from here and you get minus, so delta V by Z current flows through this. So you could replace this with the circuit. So if you have anything that is, these sets are basically coming in series. So your two LC tanks can now get replaced by a single inductor, single resistor and a single capacitance. Quickly tell me the values. If you had L here, this would be 2L. R becomes 2R and C becomes C by 2. What about the cross-coupled transistor pair? So I can apply, so I'm applying a test voltage here and I need to find out how much current is flowing through this. So let me assume, let's say Vt is applied like this. Let's say this is some plus Vt by 2 and this is minus Vt by 2. What is the current flowing through this? Minus GMVT by 2. So the current is, because the voltage applied here is minus Vt by 2, you will have current flowing in this direction given by Gm times Vt by 2. What is the current here? In this direction you will have right. So the current flowing through the source is in this direction given by GMVT by 2. Right. So if you do Vt by It, you should get minus 2 by Gm. Any confusions on this? Okay. Now what is the condition for oscillation? What constraint do you have on GMRP? So the total gain in the system was GMRP the whole square. What is the exact condition for oscillation? This should be equal to 1, right? Which means GMRP should be equal to 1. So then you would design such that your Gm is equal to 1 by Rp. So this becomes minus 2 times Rp. Right? So now let me put the whole circuit together. So I have a resistance here. Given by minus 2 times Rp. I'll simply rearrange the components here. Let's say I first have the inductor followed by the capacitance and then the two resistances of value 2 times Rp and minus 2 times Rp. Right. So at omega naught, what is the value of this portion?
Infinite.
This goes to infinite, right? Again at omega naught, what happens to this? This is also infinite, right? Which means the overall impedance of the circuit is now infinity.
So it can oscillate.
Right, but just wanted to point out that at omega naught, the impedance associated with it is going to infinity.
The proportion.
Which portion?
In below, proportion infinite.
How this L and C became infinite. So this is now simply an inductor in parallel with the capacitance. So if do you remember how this looked like? For an LC tank, at omega naught, the impedance was infinity. That's it.
Even the bottom circuit, why can't you have the half circuit concepts to find the impedance?
Okay, how would you apply the half circuit concept?
All the nodes on the line of symmetry and the zero voltage.
Remember that
So if you apply Vt voltage, the voltage appearing here is minus Vt. So if you recognize that and apply that in the half circuit, then it is fine.
I'll take that into account.
How were you planning to do the half circuit?
Like I was initially planning if the circuit is symmetrical, every nodes along the line of symmetry has zero voltage.
But is this node in the line of symmetry? Yeah, they are not shorted. Right? But you can still, if you recognize that they are, one is Vt, the other will be minus Vt in the overall operation, then you could have still written Vt and minus Vt and solved for it. And then put, basically doubled the impedance. This would give you minus 1 by Gm, and into 2 will give you minus 2 by Gm. Okay, so we have done with a single-ended common source amplifier with a tuned load. So next topic is to take a differential common source amplifier with a tuned load and see how that is going to oscillate. But that will, so you'll take a differential common source amplifier but with LC tank. Differential amplifier, right? But with, so something like this. Right, and then we will see how to get this to oscillate. I want to give you one more homework just to think about how certain operations are happening. So let's say I have a parallel RLC circuit. Assume that it is going to oscillate at omega naught, and I inject a current at omega naught, right? So if I look at In as a function of time, this is going to be some A naught into sine of omega naught t. Can you think about what the potential and the current through each of these components is going to be? Right? So potential.
I into that R. Potential.
Potential is that, right? What about the currents in each branch?
The whole ion current goes to that R.
The whole ion current flows through the R. What about the current in inductor and capacitor?
There are individual current flowing.
How would you, what would be those values? So you have to look at this at omega naught. Right, but even if you completely don't know, I mean, you know how to define quality factor now, so you should be able to derive it from scratch. They have to be phase shifted because the potential across all three are same. Current through the resistor will not have any phase shift with respect to that potential, right? So inductor and capacitive currents have to be phase shifted.
Just writing the S term, the 1 by SC and 1 S omega, we know already the potential over there. So I equals to V equals fire.
Right. Yeah, this is not hard, but I just want you to be familiar with the currents. So I want to see the time domain expressions for the currents. Yes. Let's discuss.